Today's topic: the highest number of factors any number has in a given range equation. An equation derived by me, Sergio Fernandez. I always start my videos by actually showing the equation, which is going to be the topic of the video I'm making. This is the equation which I'm going to be talking about today. It's an equation I derived because I wanted to come up with an upper bound for an earlier equation I had made, an equation which tells you the number of factors of any given number. As it turns out, once I made this equation, I realized that this equation is very closely related to another equation which seems to be a topic which a lot of people are interested in, the highly composite number equation. With one simple modification of this equation, you get the highly composite number equation. They are basically the same equation with one simple difference. I'm going to explain to you why a highly composite number is important and how you could modify this equation to actually get the highly composite number equation. What is a highly composite number? A highly composite number is a number that has the greatest number of factors than any number that came before it. It's kind of like the opposite of a prime number. For example, let's look at the highly composite number of 7. We have to look at every number between 1 and 7, see how many factors it has, and then pick the one that has the greatest number of factors. For example, 1 has 1 factor, 2 has 2 factors, 3 has 2 factors, all the way to 7, which also has 2 factors. Now, looking at all the factors, we realize that 6 has 4 factors, which is the greatest number of factors in that range. So the highly composite number of 7 is 6, because between 1 and 6, 6 has the most factors of every number. Now, why are highly composite numbers important? Well, as it turns out, highly composite numbers play an important part in our everyday lives. Clocks use 60 minutes to measure the time because 60 is a highly composite number. 360 degrees is another highly composite number, and it's the basis of measuring circles, again, because it has so many ways to divide it evenly. Even as far back as 400 BC, Plato pointed out how highly composite numbers were the ideal numbers for city population and land distribution, since, once again, there was so many ways to divide land and to distribute things evenly among the city's population. Okay, this equation, the topic of this video, is actually a very simple derivative of an earlier equation I had created in another video. It is closely related to highly composite number in that it finds the highly composite number, however it doesn't return the value of the highly composite number, but it returns the number of factors that that highly composite number has. For example, let's look back at our original example of the highly composite number of 7. Again, we look at the numbers between 1 and 7, we look at all the factors, and we realize that 6 has the most number of factors in that range. It has 4 factors more than any of the other numbers. Now, the highly composite number equation is interested in the number 6. It will return, in this case, the number 6. My equation, since I was looking for an upper bound, I was actually interested in not even getting back the number 6, but getting back the number of factors 6 has. So my equation looks at the numbers between 1 and 7. It finds the number which greatest factors, which is 6. But instead of returning 6, it returns the number of factors 6 has, which is 4. So my equation will return 4 instead of 6. Now, the tweak that you have to make to my equation to go from it returning 4 to it returning 6, it's a very simple step. But again, I was not interested in the 6 because I was looking for an upper bound. I was interested in my equation returning the number 4. Okay, in order for me to build this equation, I'm going to have to use some other equation as building blocks. So I'm going to use, for my little bag of tricks, my number of factors equation, and an equation I got from the internet that gives you the maximum value of a set of numbers equation. Okay, so now I'm going to show you how I arrived at the equation. So to start off, we're going to take this equation, an equation I came up with earlier. This equation returns to you the number of factors of any given number. I'm not going to explain how I got to this equation since I already wrote another video explaining in detail how I got to this equation, but I will put the link to that video at the comments at the bottom of this video here. But this equation pretty much tells you the number of factors of any given number. This is the same example I've been talking about for earlier, the highly composite number of 7, but in a visual way. That equation that I showed you previously will give you these values, which is the number of factors of any number between 1 and 7, as I put it in this example. For 1 it gives you 1, for 2 gives you 2, 3 gives you 2, 4 gives you 3, etc., etc. Now, if you look at the numbers, at first, they just look randomly going up and down. They don't seem to follow any particular pattern. But the longer you look at the equation, I mean the wider range of numbers that you look at it, you begin to notice something. They'll begin to pack tightly, and the top kind of forms this kind of smooth curve. Now, if you keep on going out there just for a very large amount of numbers, pretty much all of this will become a solid region, with the top being this very smooth curve on top. You could try it yourself. This smooth curve, a simple equation to display this smooth curve serves as a very tight upper bound. This upper bound I was actually looking for because someone asked me for an equation for this upper bound. I noticed that a nice upper bound actually touches just on all these high points, and these high points are the highly composite numbers of all the numbers between that range. There's a lot of methods to come up with an approximate curve, to come up with this approximate curve. The problem is that if you take all this data and you feed it to a lot of these methods to come up with the approximate curve, because you have all these low numbers down here, it throws the curve off, and you actually end up getting with a curve that actually goes kind of through the middle of all these numbers, which is not what I want. So I wanted to come up with a function that would just keep track of the highest value so far and throw away all these little low values. Again, the original equation from 1 to 7 would tell you 1 has 1 factor, 2 has 2 factors, 3 has 3 factors, 4 has 3 factors, 5 has 2 factors, etc., etc. The new curve I want a curve that actually remember the highest value until that point and just remember that value. So looking at my red curve, this is what I want to modify my curve to. For 1, I want it to remain 1. For 2, I want it to remain 2. For 3, remain 2. For 4, remain 3. But for 5, when it dips down to 2, I want my function to say, even though 5 is 2, up until this point, the greatest number of factors I found so far was 3. So I want 5 to also return 3. So this is actually the highly composite number equation. But instead of returning instead of remember the 5, it's remembering the number of factors, which is what I told you. So this is the equation I want. If you use this equation and you keep on going, you'll notice that it always has this nice, extremely tight upper bound. So how do I go about remembering the highest number of factors up until this range? Up until this range, up until this whatever range. A nice little way to do it is basically if I take all these numbers and I find what the maximum number is, that maximum number is the value I want to remember. For example, 7 goes back down to 2. I don't want my function at 7 to return 7. I wanted to remember that the highest number found so far was 4, so I wanted to return 4. So how do I keep track of the biggest number in a range? I've got this formula. It's not a formula that I derived. It's a formula that's existed for a while. There's actually a lot of proofs online which you can find. I'm not going to go too much into detail over this. I'm probably going to make another video explaining it, although normally I don't like to explain other people's equation. I like to explain the equation when it's originally mine. But just a brief overview. This equation, you give it a set of positive numbers, any numbers at random, 1, 5, 7, 2, whatever, and by taking that number, raising it to a very large power, adding them up, and then taking the root of that same large power, you get it returns to you the maximum value. Actually, ideally, it will be as the number goes to infinity, but it actually could be just a large number. It works pretty good with which large when a number is large enough. So basically, it does what it says. It gives you the maximum. If I say 152, plugging it in will return 5 because 5 is the maximum. Again, I'm not going to go too much into detail because this is not my equation, but I will probably put another video explaining how the equation works. But using this equation, I got a tool of keeping track of the maximum number of factors in a range. All I have to do pretty much is take that function and replace the set of numbers with the result of my function between 1 and the given range I want. So instead of having just random numbers, I have the value that my function returns for 1, that returns for 2, all the way up to x. Okay, doing this, I could start simplifying things a little bit. Because I'm actually having the sum of my original function from 1 to n, I could simplify this by using the nice little sum function and get this out of it. Okay, so I could have the sum from 1 to x of the function. Again, raise it to infinity and then square root of infinity. Somebody didn't understand what infinity means. If you don't like to think of the concept of infinity as a number, just think of it as a limit. The limit as the number gets bigger and bigger and bigger. So you could take this number, make it 100, 200, 300. As it gets bigger and bigger and bigger, you'll approach your ideal value. Although you don't even have to go that far. Just, I think with 200 will be very good enough to get you the exact answer. Sometimes even lower than that. But what was my original function? Well, replacing f of x with my original function, which was this sum function which returns to you the number of factors of the equation, I get my final equation as this. So the maximum from 1 to x is this equation, and this equation is the equation I was trying to arrive to, my final equation. This equation, as I explained, what it does is that it gives you the number of factors of the highly composite number of the given range from 1 to x. So if we take that equation we came up with and we just keep on plugging it to more and more x's, it does just that. For 1, 1. For 2, 2. For 3, 2. 4, 5, whatever. When we get, let's say, to 16, it looks at all the number from 1 to 16. It finds that 12 has the greatest number of factors, which is 6, and it returns 6. So it starts generating this kind of nice little very tight upper curve, which begins to actually look, as you spread out at the beginning, like a kind of like a step ladder. So if you keep on going and keep on going, it keeps on remembering the highest point. Now remember, I told you something. I told you that this function was related very closely to the highly composite number equation. If you look at the equation and you see what points it's keeping track of, this point is keeping track all the way up to there. This point is keeping track all the way out there. This point. If you look at this point, you realize that these points actually correspond to highly composite numbers. 12 is a highly composite number, and so that's no wonder. It's the number that we use to measure rulers. So if you keep on going, again, it keeps on creating this nice little function. It keeps on creating this extremely tight upper bound. And the upper bound, as you keep on going, keeps on creating that curve, but actually does a better job than the curve because it's so tight. It actually looks like a ladder, actually. So if you keep on going, that is the tightest bound we could have. So although the original equation was meant to be an upper bound, the points that it's keeping track of are the highly composite number points. So at this point, I have my new equation. I could get rid of all this chaos behind and see what my new equation looks like. Okay, so this is my equation. It's not so chaotic going up and down, up and down. It's a nice little ladder going up, and if you keep on going out to infinity, it actually stops looking like ladders and it actually starts looking like the smooth curve that we wanted to. Again, I originally came up with this equation because I was looking for an upper bound to the number of factors of the highly composite number equation I had. To the number of factors equation that I had come up earlier, and this equation, which I derived from that, turns out to be the number of factors, the number of factors of the highly composite number in a given range equation, which is something a lot of people have a lot of interest in. Although I was interested in the number of factors the highly composite number has, most people are interested in what that highly composite number is itself, not the number of factors. With a simple modification of this equation, you could actually derive the other equation that a lot of people seem to be interested in. But this video, I think, is just going close to, it's over 10 minutes long already. So I'm going to put up another video explaining how you could modify this equation to get the actual highly composite number equation. Again, this finds the highly composite number, it finds the point, but it returns to you the number of factors. A simple modification will change this so that instead of returning the number of factors, it will actually return the number, which is the highly composite number itself. Okay, guys, thanks. And we'll see what other interesting equation I could derive from my original equation that I had put up.